Every sleek smartphone and laptop relies on a hidden foundation, a printed circuit board. These boards are complex chemical sandwiches engineered to hold thousands of microscopic electrical pathways in perfect alignment. For decades, the structural integrity of these boards depended on a chemical hardener called dicyandiamide, or dicy. Vintage assembly lines from the 70s and 80s produced boards almost entirely cured with this single compound. This table compares the properties of different circuit board resins. Look at row 6, detailing mechanical properties and adhesion. Dicy was cheap, but more importantly, it acted like a molecular rubber band, possessing high flexibility and bonding flawlessly to copper and fiberglass. The rapid growth of early consumer electronics was built on the structural success of this single chemical bond. When environmental regulations required the removal of toxic lead from electronic solder, the industry's thermal requirements were rewritten overnight. This spec sheet outlines the lead-free reality. Traditional solder melted easily, but these tin silver-copper alloys require intense oven temperatures, between 217 and 220 degrees Celsius, to form reliable connections. Under that kind of heat, dicy-cured resins break down. The polymer chains crack and release trapped gases, causing the fiberglass and copper layers to violently rip apart and blister. This move to protect the environment inadvertently destroyed the structural integrity of the circuit board, forcing a complete redesign of polymer chemistry. To create a solid board, liquid epoxy resins require a hardener to act as a cross-linking agent. This hooks loose molecules together into a rigid, three-dimensional grid called a thermal setting polymer. To survive lead-free baking temperatures, chemists replaced dicy with phenolic novolac hardeners, or PN. This created a much denser, more tightly clustered molecular architecture. PN hardeners have low chemical polarity, meaning they naturally repel moisture. Without water trapped inside the grid, there is nothing to boil and expand when the board enters a 220-degree oven. But solving the heat crisis created a mechanical one. PN hardeners lack dicy's flexibility. The matrix cures into a highly rigid, glass-like state, making the board brittle and prone to fracturing under stress. Surviving the oven meant sacrificing structural toughness, trapping material scientists in a loop of engineering compromises. The first chemical intervention involved multifunctional epoxies. As these diagrams show, instead of simple linear chains, these molecules grow intricate branches that boost the material's baseline heat tolerance. Next, chemists pack the resin with inorganic fillers. When oven heat forces polymer chains to expand, these rigid particles physically wedge themselves between the lines to lock the structure in place. This addresses the z-axis coefficient of thermal expansion. Minimizing this vertical swelling is critical. If the board expands too much, it will snap the delicate copper pathways hidden inside. This microscopic cross-section shows the final hack to the shattering problem. Those glowing white particles dispersed through the blue resin are an organic filler known as core shell rubber. These rubber spheres act as microscopic shock absorbers. When a crack forms in the brittle matrix, it hits a rubber core, which compresses to absorb the energy and stop the fracture cold. Modern material science is a cascading series of patches, where every chemical solution requires a subsequent structural fix to maintain balance. Modern FR-4 resin is a precise cocktail of base epoxies, PN hardeners, inorganic heat shields, and microscopic rubber terminators. Compare this modern manufacturing facility to the assembly lines of the past. The forgiving chemistry that built early computers has been replaced by a sensitive process with near zero margin for error. In industrial chemistry, there is no perfect material, only an aggressively optimized equilibrium of opposing physical forces. The silicon computing power in our devices relies on a violent chemical balancing act occurring inside their plastic foundations.